In this episode, we discuss digital transformation through digital twins. My guest on this episode is Dr. PG Madhavan. PG has deep expertise in data science, and he has previously worked for companies such as Techolution, NEC Corporation, GE Aviation, Microsoft, and Rockwell Automation, among many others. He's also worked as a university professor at the University of Michigan, Indiana University, and Waterloo University in the departments of electrical engineering and computer science, neurology, systems design, physiology, and biophysics. A quick thank you to our sponsors. This episode is made possible by our friends at HiveMQ, who are providers of an enterprise-grade edge and cloud-based MQTT broker. So please do check them out to help support this podcast. Welcome to the Fourth Generation Podcast here on Industry4.tv, which is a series of weekly interviews designed to help you learn industrial IoT from some of the world's leading practitioners. So if you're new here, please make sure to subscribe and click on the notification bell so that you never miss any of the interviews. If you find this conversation interesting, please review it with 5 stars on Apple Podcasts, follow on Spotify, and you can also connect with me on LinkedIn at Kudzai Manditereza. Now, here's my interview with PG. Okay, so Dr. PG, I would like to welcome you to the show.
Glad to be here. I know you have a broad but focused audience, so I'm delighted to address them on some of my pet topics like IoT and digital twin. Thank you, Kudzai.
Thank you. So today I want to talk to you about digital transformation through digital twins. Now, digital twins is not a new concept. It's been around for some time. However, we have seen renewed enthusiasm in the last couple of years. And yourself being someone who was involved in the early digital twin projects, what makes you more enthusiastic about digital twins today than before?
That's a very good question, because early on, back in 2000, when I was involved in developing probably the first large industrial IoT, there were small POCs and others before. I learned the hard lessons, and then I realized there is something missing. So if you have seen some of my articles, I have this picture where I show an IoT arc that's improving, but in the middle I have a kink. So the story behind it is as follows. Right? Let's start at the very beginning, turn of this century, 2000. I'm at the Georgia Pacific plant. Georgia Pacific is one of the large paper manufacturers in the US. So, the paper, there are thousands of rollers where the paper is just, sucked out from the pulp and made it in newsprint at the end, the big rollers. So there are things that happen which before that time, maybe decades before that time, was basically breakdown maintenance. Something breaks down, the line goes down, you got to go fix it. It is, in this case, probably only a few hours, work lost and some cost associated. But in some of them, breakdown maintenance is huge. I remember a case where Nucor, I believe it is in Cleveland, it is one of those days new type of steel mills, mini mills. So they make mostly sheet metal for the car body parts. Those days, car body parts were metal, not plastic like today. So they roll these steel sheets, which are, I don't know, height of a house, and then it is kind of wound together, and there are direct cranes that will take the finished product and move it to the other end where they load in the truck. Talk about a breakdown maintenance. One of these big rolls of steel, as it was going, that binding broke, and you can imagine the force, the energy that is in that roll thing. It just exploded. It just broke the big steel beams and posts like matchsticks. Wow. So this is a case where they probably lost 3 months of work. They had rebuilt the thing. So from breakdown maintenance, people realize not a very good thing. So they started going towards what's called preventive maintenance. So before things happen, so in the Georgia Pacific case, now they said, okay, we'll put grease in the joints every week, right? Preventive. So it'll get lucky. Now, then they realized, well, you can do better. You can do predictive maintenance. So if we knew when these things are going to or tending to fail, let's only apply the grease at that time. So you're saving some grease, and it seems to work. Now, so far, so good. This is where now I think the kink happens. So now if you want to go beyond that and say, okay, now should we just depend on these predictions of when the bearing needs to be, made less friction, made friction-free? Or is there something other than that we can do to this process change so that there is more paper produced with less waste and of higher quality? The IoT digital twin systems that can address that is what we call prescriptive analytics. We have not gotten the prescriptive maintenance, for example. So the objective is not really maintenance. It is really taking it beyond and then improving the functioning of a plant. So it's like a long story, but I believe you're at the threshold of being able to do prescriptive maintenance and analytics, which goes beyond just maintenance and affects performance of the plant. So I think it is a very exciting time. One of the keys in doing that is something called causal digital twin, which hopefully we will touch upon. It's a really hard topic, but important. And then, so far, we've been treating symptoms, as I call it. Now we are at the threshold of addressing causes. That's why I'm so excited.
Now, most advanced analytics use cases, they consider predictive maintenance to be a low-hanging fruit, and hence we see it being applied and being mentioned everywhere, which kind of gives it the notion that it's like a killer app for IIoT, and you strongly disagree with that notion. Could you explain to us why predictive maintenance is not the killer app for IIoT?
Low-hanging fruits usually are not killer apps. They are the way to entree into a field and get your whereabouts. Then you have to expand. And let me give you another story, again, from, say, this paper plant. Right? So before we deployed our solution in 2000, what people would do is, walk around with a handheld computer type of thing, specialized equipment, not an iPad or anything. There was no iPad then. And there will be a tether, a wire with some sort of various sensors, temperature sensor, pressure sensor, vibration sensor. They'll go and stick it in each of these rolling elements and collect all this data, go to the office at the end of the day and dump all the data into a kind of a spreadsheet. So what we did was we came in and said, look, this is a good thing. You're doing something towards preventive and perhaps predictive maintenance, mostly preventive. But instead of just walking around, it's a very labor intensive and unreliable. To be very frank, some of these people who walk around and do this don't do it very diligently. If you have to do good analytics, the measuring point should be the same every day, every time. They don't measure every day, maybe once a month. It has the same point, and they don't bother to do it. So you're getting really mixed up data, very hard to make any sense of it. So we said, we'll attach these things, then bring that data through a wired thing to what we used to call CPE, customer premises equipment. Today we'll call it edge computing. So that edge computing has wireless connectivity to the office. And so it goes into the PC and then it comes to our servers. There was no cloud at that time. And we would do this analysis. So, and we also introduced a concept of a visual digital twin, so that instead of just looking at these spreadsheets, I said, It'll be much better. And lots of the customers even kind of push back, saying, we don't need it. We know how to do these spreadsheets. I said, no, I'll show you something better. So we would take digital camera pictures of the plant floor, and they can flip it on the computer screen. And wherever there were measuring points, it'll either show green, yellow, or red. And then they click on it, they can actually see the spreadsheet. So they can look at history. Then they click on it one more time, you can actually see the real-time vibration data, temperature data coming through, including the spectrum. So it became actually a huge selling point. So the first time we deployed it, and plant folks were excited, the engineers were excited, the executives were excited. Everybody's doing great. Now, 6 months later, a year later, when I visit them, the level of excitement has kind of subsided a little bit. So the question was, what happened? So they were saying, we spent X million dollars on this. So the CFO was asking, so what happened? Did you increase production? Did you, better qualities? Did something happen? You see, this is where now finance has to come in. So the way financial statements work in companies are the top line items and the bottom line items. Top line items is the gross margin revenue. So gross revenue, COGS, cost of goods sold, and the difference is the gross margin or the gross profit. That's what people see immediately. Now, below the line, there is a lot of crap. There is interest and payment and this and operations and blah, blah, blah. Maintenance happens to be under the line. So two problems. One, executives almost miss it. Number two, when you put these things in, how do you show that you saved some money? So here is the problem. So let's say because of this, this bearing didn't break. Now, somebody, smart guy, like in the customer's team would ask, well, how can you attribute it to a classic attribution problem like in advertising? How can you attribute it to your software? Maybe it would never have failed. Now you can say, okay, now let's do an experiment. We'll compare this plant to another plant. Then they will say, plants are so different. And obviously in industry, you cannot do like control trials. You cannot do statistical comparison. You can't even do pre-post. So let's look at last year, what was the expense this year? So many things have changed. The raw material going has changed, plant laborers have changed, all those things. So it's just impossible to convince them that there is no perceptible improvement in the top line. There is nothing really visible under the line, and there is nothing we can convince them that we have actually saved $10 million. It is just back and forth with no real resolution. So the excitement of the CXOs, CFOs, and others, start diminishing, and that pervades through the company. Now they're less excited, so the plant superintendent is less excited, and the foreman is less excited. So that's why I say it's almost like a must-have. It is like brushing the teeth in the morning. You have to have predictive maintenance. You cannot do breakdown. So that's a given. But anything more than that, and people are willing to put money into that at a certain level. But any other investment, you got to show either increase in revenue because you're producing more, or reduction in costs, you're less cost, less raw material, or the quality is better, so you can charge higher for the same thing so that your gross margins goes. That is the killer app. And that to me will happen only when we get to that other side of the curve that I talked about as prescriptive analytics.
So I intend for us to dive deep into the application of digital twins in industry. But before we do that, I would like us to set the foundation. Maybe if you could describe to us what is the central purpose of a digital twin.
So, there are so many associations and consortia who are involved in this, and they have their definitions, and many of them has to do with somehow reflecting the physical twin various details onto the software entities that you can see. I think that's too narrow. So my preferred, and I try to zoom out, I look at it from a value perspective. To me, what a digital twin does is take local information from wherever, bring it all into a global picture, integrate that picture, not just show local pictures, but integrate them. How do they all work together? And then based on that, you say, do these local actions so that we can achieve a global business goal. Because business goals are global, it's not local. Let me give you an example. This is too fuzzy. Smart city example. Let us say the local measurements are video analytics camera at each of the junctions, where there is traffic signals, right? So that is the local information. So this all bubbles up to our smart city digital twin. Now, if you have just all these things, you can show on a map, there is delay here, so it's red, it's flowing smoothly, it's green. Okay, great. But we have to integrate something. And that is where the real value is. So if we can then say, okay, if we change dynamically the time that this intersection stays red and this intersection stays green, this flow would get better. Now, what are you doing? You're integrating the information to a higher business goal, in this case, smoother traffic flow. People feeling happier because they can get to work easier. There is less frustration. Those are fantastic business goals because it'll translate into something good. So now, from that global picture, then you say local action. So you send down information to control those lights. Delay this, do that. To me, everything that you see today in digital twin can be mapped to this framework that I mentioned. Take local information, integrate the global picture. From there, find the global business advantage and prescribe local actions. That loop is, to me, what digital twin is. So to do that, there is all kinds of, you have to have all that IoT connectivity and, local or WAN connectivity, and you have to have the software platforms, you have to have the security. So all of that is getting the stuff. Then you have to have a stack where you are storing past, instances and the current instances. You're looking at differences. So all of that, so whole software stack, all of those things are the details that are important. I actually have a block diagram where I kind of put it in like 2 or 3 pieces. I talk about it as, the way to realize this broad picture that I kind of painted is through, get the data and condition the data. That's one piece, and we know how to do it now very easily. Then I talk about it as a condition or thresholding or detecting section. Then a visualizing section, and then an important middle section, which I call root cause or what if analysis section. That's where the global business goals gets translated into local actions. And then this is fed back. So this is, to me, what digital twin is. A little fuzzy, but that is a good level to define digital twin, because I see it as a framework for a variety of things, including digital transformation, which is the big buzzword these days. So if you generalize like this, it's broadly applicable. And in specific cases, we know the block diagrams and the stack.
So, as you have rightly pointed out, that idea of bringing information up to paint a global picture involves bringing together a number of digital technologies. And so what do you see as being the biggest challenge in integrating these different digital technologies to realize the digital twin?
Actually, there is a very pragmatic way to approach this. I'm sure every major hyperscaler has a similar kind of a progression chart. But I remember seeing AWS has a 4-stage digital twin thing. They call it L1, L2, L3, L4. So when you first get into this, you don't have to have all of these things and what if analysis and all that stuff. You can do step by step. There, L1 is just collecting the data and displaying it in the dashboard. something very simple. The next is, I don't remember all the levels, what they do, but it's increasing sophistication. So L2 is probably they do some automatic thresholding. If it is vibration coming, if it is exceeds something, set off an alarm or send a push notification to somebody on the plant floor, blah, blah, blah. So that is kind of L2. And L3. L4 is where that, what I just described, that big picture, bring it to the global, think about business objectives, and then do that. That's 4. So there is no reason to do L4 first. You can start with L1. Simple technologies today. Wireless is no issue. There are so many LoRaWAN, NB-IoT, LTE. There's so many options available. Sensors are still a problem, especially if it is battery operated. Those technologies are also kind of improving. Now, once the data comes, there are just AWS, Azure, Google, not so much they're exiting, but there are so many other proprietary and smaller IoT platforms that can get this data in and massage it and show it in a nice digital twin or dashboards. I still have a little bit of a, pet peeve about the dashboards. Dashboards today typically just show a dial with this thing here and a bar chart here, blah, blah, blah. I would any day recommend a digital twin I created way back when. Remember I was talking to you about go take digital picture of the plant floor. So it's very human, that user interaction, and people just loved it. It was so cool. So you see the picture, if something there, you can go down and see it. So I call it a hierarchical visual digital twin. So I wish instead of just dashboards, it's an easy thing to do, because you just feed it. There are CMS and other things available. You can just put it in and you see this picture. But if you can do it in a more human way, visual, then you can drill down technical, drill down even more. That would make a wonderful, not dashboard, but visualization. Now, in future, I suppose it is AR, VR, XR. So that is probably where there is still some challenges. And of course, the middle part, the root cause analysis part, is not addressed. I don't want to say at all, but very rare. So that is where the technical challenge is. But there are glimmers of hope. There are tools available. It's not prevalent, but that I'm sure will come in the next 6 months to a year.
So now what I would like us to do is to hone in on the industrial IoT or IoT aspect of it. Can you break down for us what the role of IoT is in digital twins?
Again, sometimes stories are the best ways to explain what to do. So I had spent some time at GE Aviation, and that's a place where, GE Aviation have like 40,000 jet engines in the air every day, at any instant of time, I think. So, they have the production part, the operations part, the service part, and all these things. So GE Aviation, I'm not, divulging any proprietary information here. Any major corporation is doing this, but during production, there is millions of parts that go into a GE NX or one of those big engines that you see. And these are all tagged, documented. I don't know whether there are RFIDs, etc. Those are specific internal details, so I won't get into it. But these are all captured. And then when they're all put together and then it's hung on a wing somewhere, those things are tracked. And when they're in the air, it's continuous data being sent. So there are sensors in the jet engines for all kinds of things. There are tons of them. I used to work on a specific one, a very difficult high temperature sensor right inside the hot bath of the jet engine called T3. So all this data, in olden days, they would just have little snapshots they collect and then download it, I think maybe through satellite. But now there is something called CEOD, which is continuous data. So continuously measure this. And generally it is download it when the plane comes to the jetway, and there is a hotspot where they just dump all the data very quickly, and it comes to GA Aviation. So they have, like a NASA control room kind of various things, I believe. But here is a step-by-step way where you capture all of this. And when all these information along the whole path is captured, and the engines go through these, maintenance and rebuild and cycles, then they go back on again. So all that is captured, and that's called the digital thread. So digital twin, in my opinion, includes the digital thread. So if you want to look at an engine with a certain problem, you can click on it and see. Then you can go down and see the digital thread. Who built that sensor? Then when was it installed? When was there any repair or replacement? So they see the whole digital thread. So this is typically how digital twins, to me, come into play in an industrial IoT use case.
Okay, so now moving on to the machine learning aspect of it, can you tell us about the machine learning methods that are used in digital twins?
Yeah, this is my pet topic. In the last so many years, decade or so more, I've mostly focused on machine learning of various aspects. When it comes to industrial IoT and applications that you and I care about, and probably the audience care about, I'm in Andrew Ng's camp. Most of you will know Andrew Ng. He's the machine learning professor from Stanford, and then he has gone on to do things at Google and Baidu and all of that. But his Coursera course on machine learning, I've done it. I'm sure you've done it, and majority of these people have done it. So recently, there is always this buzz about deep learning and identifying cat versus dog and natural language processing and all that. Those are big data. So Andrew Ng is for about small data. So he has a whole investment fund, and his own advisory activity is all about applications, not in consumer space. Well, that's nice. That's important. It's good to know a cat from a dog. Those are all great. But he wants to apply it to where there is, I assume, wealth is created, things are manufactured, real stuff happens. And he was saying in those cases, you don't have billions and billions of data. When you need to train a natural language processing system, the corpus of data is billions of words and pages of all kinds of things from wiki and UN transcriptions and in every possible language, right? We don't get that kind of data. When I was doing the jet engine work for the temperature sensor, it hardly fails. Otherwise, these planes will be falling out, right? So the amount of data, especially abnormal data, is tiny. And in comparison to the general or the consumer application, like NLP and what you hear for image processing and so on the consumer side, the amount of data is tiny. So that's what it means by small data. So in these small data cases, what are the machine learning tools that work? Actually, deep learning, I haven't seen any significant application other than maybe one in some inspection of the blades of a jet engine fan. I take a picture to see if there is any, not cracks, but even a little tiny thing when the plane lands. You can quickly do that while it's staying in the jetway. Then you can see if there is a problem or not, perhaps. But they're very, very small. So the machine learning techniques that apply in our domain is usually just the regression and classification, the good old stuff, right? And multi-layer perceptron neural networks. So not deep, but maybe 2-3 layers, maybe whatever width it is. And one thing that I'm hoping to see will happen is what is called SVAR. It is structural vector autoregressive processing, because that is, when you think about almost all IIoT, industrial IoT applications, what you're doing is sensing from many, maybe thousands of points, sensors. All the data comes. Now, if you treat each data as something separate, you only get, I call it like looking through straws. You're just seeing one thing because they are all related. If you have temperature, pressure, vibration from one part of the machine, they all are related. They have connections. We are not seeing it if you just process separately. Now, all the connected things in the paper processing chain, they are all interlinked. And we don't see that if you process. So if you have to put them together to analyze, not if, we have to. And there's techniques available in advanced machine learning and stochastic process things. It may be mathematically hard, but the algorithms are readily available. It's maybe already available in Python, but it's in so many open source. I have open sourced many of them myself, because that will lead to analyzing causality, these relationship between these various single channels of data that you collect. That's when you go to the next step. If you think of that smart city example, traffic, all those lights, let's say video analytics that come from each, are not independent pieces of information. They're all interlinked because the traffic is being held up by each other. They are affected by each other. So they all need to be combined. And that has not happened. And I think that is the next big machine learning activity. So I have a little triangular pyramid that I use. I say simple thresholding kind of thing is good for just knowing condition monitoring. If you use some small simple statistical methods like regression, machine, multi-layer perceptron neural network, and so on, it'll be good for predictive maintenance kind of thing. But then you need a causal analysis or causal machine learning, and that is becoming a topic now. That is what you need for this high-value prescriptive analytics, where you can do root cause analysis and what-if analysis, counterfactual, as we call it, analysis. So that is yet to come, but it's imminent.
Maybe let's focus on the application of root cause analytics method in digital twins. Can you maybe expand on that, on exactly why we need it and how it works?
See, this is a classic difference where when we don't go to the plant floor and actually see how things are done, how our mindsets sometimes are not aligned. In that 2000s, when I'm on the plant floor at Nucor or Georgia Pacific, let's say, some breakdown happens, something seized up, let's say a bearing, and that thing gets replaced. But that's not the end of the story. The vibration specialist, the operator of that part of the machinery, they all get together and they do a root cause analysis. They will get together, and those days we didn't have all these mathematical techniques. They may set something up in the lab or something and run it to failure, or put loads on it in certain ways, or the shaft is slightly misaligned. Then they can see what is happening. You know why? Because you don't want to treat the same symptoms again and again and again. You want to solve it so that you don't have to do this again, predictive maintenance or preventive maintenance again. So root cause analysis is an integral part of fault detection. When fault is detected with your software, that's not the end of the story. You have to have that next step so that you're not treating the symptoms again and again. So you have to solve that. And that is not, again, being done. And for that, the real fundamental need, so this is the whole underpinning of causality. Some people would say causality is the most important relationship in the universe. That's probably big, but cause and effect. That's how the whole Western scientific method is built. Our laws and even social interactions, it is all predicated on this. There may be other better systems, we don't know, but that's what we have today. When something happens, something happens. So if it is in a law or criminal case, that action caused this negative impact, then you are liable, and you have committed something, felony or something like that. So cause effect is so important to know. Without that, you can't find the root cause, because you have to repeat that and solve the same problem again and again. So root cause analysis is simply a fundamental important thing. Now, again, this is not to say, people are not getting it. No, I see this as a natural progression of the field. We came from, like I said, breakdown maintenance to preventive maintenance to predictive maintenance to prescriptive maintenance. It'll come, but we are at the threshold of that next stage. And I believe what I'm talking about is what's coming soon. It's imminent, because people realize that you can't do all of it at one time, especially for root cause analysis. The methodologies are actually quite, what shall I say, hard, but
complex.
Deep learning was hard, and this was hard. But now there is you take a Keras or PyTorch or something, and boom, put together, there is the result. It'll happen very soon.
As you have explained, that this principle of causality can be applied to different types of data. So can you speak to us about its application in industrial IoT data in particular?
So what I just talked about, that root cause analysis, that's very clear, right? You had to, whenever there is a failure, you got it. That should be the mindset, and the software should allow that. That's the first step. There's another step. So this is, if you think about, if you're deploying this as a like a software solution, digital twin, those simple detecting faults and predicting faults, that's an ongoing, continuous, near real-time process. Root cause analysis obviously is when there is failure, so it's not continuous. When something happens, so it's an event-driven activity. There is one which is even less often. That's what we call what-if analysis or counterfactual experiments. So this is probably when once a quarter, the powers that be get together and decide, is there anything we can do with the performance, the layout, the parameters of the process, so we can improve this thing, right? So that becomes, for example, if you want to answer a question like, okay, we grease this joint every month, right? Now, you'll get together and say, what if we grease this joint every week? Would it perform better? Would the paper be nice and thinner? Those kind of decisions. That is what if analysis. You don't know, but you have to think through and see what's going to happen. And in causality literature, what if analysis is a good term for you and us, right? But the fancy term is called counterfactual analysis. Why that is in this case, you're not applying grease every week, right? So you're saying it's not factual. So it's counter to factual. What if we have done that? What would happen? So in some of my articles on causality, I talk about one of the big names, Marletto is her name, her book on this. She gives an example of counterfactual as, would a kangaroo fall over if it had no tail? Now, you're not allowed to perform experiments. You're not allowed to go and cut the tail of 10 kangaroos, another 10 that's not cut, compare them. No, that's not allowed. So these are things that you can't do, or in the industrial plant flow, there are so many things you cannot do for these kind of comparisons and know what is going on. Now, on the other hand, in some other fields, these kind of analysis can be done quite easily and is a must. One is in drug trials. So let's say, a new thing that'll cure your headache. They do what's called a randomized control trial. So they would give to a blind group and another group, and even the people who administer the thing are blind. So there is double blind. And then, so that is real cost effect. This pill is reducing the headache by this percent in this percent of the population. Great. You won't be able to do that in most industrial, because you cannot shut down a process here and see the other process and compare the two, and losing money and various things. So that is the second big application of root cause analysis whenever it's necessary, and on a frequent basis, the what if analysis or counterfactual analysis. To me, these two map beautifully into the general conversation about digital transformation we're all going through now. So it's not just industrial, it's not just IoT. I believe that all the digital transformation that are going on today can be mapped into this, this framework. If you like, I can talk a little bit about that. That's one of my pet areas these days.
Yeah, absolutely. Okay, so well, maybe now to focus on the digital transformation in manufacturing. Can you highlight for us what you believe are the key steps to digitally transforming a manufacturing enterprise?
So digital transformation is a kind of a buzzword, right? And it's hard for people to really understand what it is. So I have a great interest in trying to reduce things to their essence, like saying digital twin. I said, taking local information globally, integrate that information, and then performing local actions to achieve a global business goal. Boom, that's so. Similarly, digital transformation, I have a larger kind of picture. I think digital transformation is two things. One is continuous assessment of what you're doing and frequent improvement of what you're doing. So continuous assessment in an industrial case is very clear. Just an industrial IoT example, you're monitoring all those data directly from sensors or from PLCs and SCADA and those things. That information is coming, you're monitoring it, you've automated all of that. Great. So that's one part of digital transformation. The other part is frequent improvement. That is like Kaizen, like the Japanese, continuous improvement. That's the whole purpose of better observability. So that continuous monitoring gives you better observability of the process, the supply chain, where the customers are going with this, how happy they are. You're seeing all of that. That is the observability part. Now, you got to do something with it. You can't just observe, right? So what is the next step? Next step is frequent improvement. It may not be continuous improvement because you can't change a process all the time. You can't change the supply chain that easily, right? So those are at appropriate times. Again, maybe a quarterly assessment. But that thing, these two maps beautifully into what we talked in digital twin. Continuous assessment is like condition monitoring. We said that's one block in digital twin. Frequent improvement is like this root cause analysis and what if analysis we talked about. So to me, the two key functions of two key aspects of digital transformation, continuous assessment and frequent improvements, map directly into condition monitoring and root cause or what if analysis of digital twins. So I think of whenever, so it's not even industrial, like I said, it could be the entire supply chain through production, through selling to servicing is encompassed in this digital transformation simplified definition. Okay. And I would apply, and some of the continuous monitoring, it may not be like continuous sensor data like time series. It could be transaction logs from a retail store. It could be some other logs from IT. It could be different kind of, but what is what is key is observability of everything that you're doing, not once a month or once in 6 months. That is what we used to do in olden days. Here, continuously near real time or real time.
So now, having established that, and maybe to sum it up, how then do you achieve manufacturing digital transformation through digital twins?
That's a kind of a broad concept, and many bigger minds than I have weighed in on it. And one of the ones that I like is Deloitte has put out a thick 50-page report on these things. So where digital twin comes in manufacturing is really what we call industrial 4.0, OT, and plus IT. There are many names. Deloitte uses smart factory, and I like that. So digital twins changing the face of manufacturing is through a smart factory. So if I just read the few things, there are 5 things they point out about smart factory. It's connected, it's optimized, it's transparent, it's proactive, it's agile. These 5 things. So let's think about that, what digital twin will do for all. Connected, of course, connected. Yes, we know that. Optimized. This is where we are talking about this what if analysis, root cause analysis, and if it's the kind of that traffic flow, you're optimizing traffic flow, you're doing that. Transparent. Don't know exactly what they mean. I mean, connected is giving you maybe it is being able to visualize it the proper way. That is probably what they mean by transparent. Or there are unknown parts of factory operations. That could be very dangerous because you make decisions based on what you see. So there shouldn't be any. So you should be monitoring everything, I suppose. Proactive, yeah, that we talked about. That is, to me, more than predictive. Proactive is prescriptive. So you do both. You proactively do things to not only prevent the same things from bad things from happening, but also act on good things to happen in the future, like increased productivity and so on. And agile. So as long as you know this visibility, you can be agile about it. So it is digital twin with people on top is what a smart factory is, in my opinion.
There is an open source project called PyWhy that you've referenced in one of your articles, which is basically causality for machine learning. Can you tell us a bit more about that? Because I find that interesting.
This is a recent development, less than a month now. I knew Amazon AWS has been working on causality. I had talked to some of those folks, mostly in Germany, somewhere in your neighborhood, Kudzai. I think it's in Berlin, the team. And there is Azure team here locally. I'm in Seattle, Redmond area. But they were working independently. And this is probably like what in during my earlier research days, there is some effort, which is sometimes, what I remember is what was driven by the government. They call competitors can work together on pre-competitive technologies. So the idea is, so mine was actually when I was at Michigan. So this is, so Ford and GM and Chrysler, and they can work on some, say, ABS, automatic braking system before it happened. They could work together because otherwise antitrust, they cannot collude and work together. So pre-competitive, they can work together. So this reminds me of PyWhy, reminds me of some of that pre-competitive, this thing, which means it is pre-competitive. It's early. It's not, ABS, it's not deployed yet. So they have their own internal works, and it looks like what this tells me without them actually saying it is that they think of it as a pre-competitive area. There is still work to be done. There isn't a causal digital twin in either AWS IoT solutions or in the Azure IoT solution set, as far as I know. But this is a great start. Now, one thing I should warn is not all of them are really suitable for IoT. So in causality, there is almost like two different branches. So one branch is what is very well known, and that is popularized by the work of a very important person named Judea Pearl. Judea Pearl is, people consider as the father of causality. He's done significant work, and his line of work, they are what you would call controlled trials. It is experimental. So his work is mostly, think of drug trials that I talked about. So there's an experiment. You can control all these things. Then you can find cause effect, right? Very important. And similar things can be done sometimes in social experiments. So if you increase the taxes on cigarettes, Will the cigarette tax consumption go down? It sounds like it, but you can perform a cause effect. Is this causing it, or is it something else causing it, etc.? So that's a whole experimental driven thing. In IoT, as we said, industrial IoT especially, we hardly get a chance to perform experiments in a real production floor or something else. So we had to work with observational studies. So it's like this IoT data that came. From that, you have to say, oh, instead of putting grease here once a month, if I put once a week, would the product quality be better? I can't go back and do that experiment many times, right? In this case, maybe, but in general, you can think of other examples where you cannot do that. But from that observational data, can you find out what is causing what? Is this effect of this lower friction improving the paper quality? Right? That is the cost effect that you want to find. So that is a very different type of methodology. And this side of that methodology is what is applicable to IoT. Now, PyWhy is also, what I have seen is there, if not everything, most is on that experimental Judea Pro type of things. So it has lots of uses in AI, in customer satisfaction and customer churn prediction, and the standard marketing research and stuff. And their data is actually different too. In those things, we call it their panel data. So each row are independent. I won't go into the technical details, but on the IoT side, each row is so-called autocorrelated, and you can't use the same techniques. Fortunately, for the IoT stuff, this method based on SVAR, so structural vector autoregressive methods. It's a work of what's his name, Shohei Shimizu in Japan, and Hyvernen, Apo Hyvernen in Finland. Done some excellent work in the turn of the century, 2005 to 2010. And again, theirs is not focused on IoT. So in the last year and a half, I've been taking their work and improving it or turning it to be directly suitable, adding some stuff called Kalman filtering and so on into IoT applications. And that software that is available. I should think of maybe contributing my code to PyWhy so people can use it. Or there may be other places. If you have some ideas, I would love to hear it. So the basic point is this: there is one class of causality studies, Judea Pearl type. So those are randomized controlled trial, or more familiar to all of us would be A/B testing. A/B testing is basically that. So that is again experimental. And the other part is observational. You can't go back and do any intervention. What you got to do the best you can. So that is what my excitement is on this side. I hope PyWhy. I hope I can add my stuff to them. I need to engage them more. Or you can always write to me, and I'll be happy to share my MATLAB code.
Oh yeah, absolutely. We'll certainly be reaching out because that's a fascinating topic, I believe, and I would believe also that members of the audience will certainly be interested in finding out more about both PyWhy and what you've been working on.
Yeah, that'd be great.
Absolutely. Now, to conclude, you've got a company called Systems Analytics Solutions. Can you tell us more about the company and what services you offer?
So I'm an engineer, electrical engineer by training. So one of the bread and butter things of engineers is what's called systems theory. We think in terms of systems. That may be confusing to some people, and this thing. But all my work is based on. So I look at even everything we do in a systems form. Systems is a little hard. You don't look at things on its own. We see everything as interconnected. And the interconnected activity, back to that. Remember, we talked about local information comes this global this interconnected information from each of the intersections or many parts of the plant, seeing it interconnected is very valuable in engineering solutions for them. So systems theory, I mean, our undergrads from even sophomore year learn systems thinking. That is, by the junior and senior year, they do multiple courses that are sometimes not called systems theory, but they're all systems theory. Yeah. Communication is systems theory, signal processing is systems theory, control system is, of course, systems theory. So it's in the blood of engineers. So that's how I think about it. And I believe it's a very powerful way. I think it's more powerful for engineering applications than even a physics-based thinking or math-based thinking. This is an integrated approach. So, well, this may be a time to plug my book. So I believe that systems thinking is so important. So 2021, I wrote a book and just published it in 2002, January, Data Science for IoT Engineers. So this is all about approach, just even basic machine learning, things like regression trees and random forests and everything from systems theory. But it goes beyond. Because systems theory, the big difference is this. In machine learning, all the data models is some sort of regression data model. So it'd be a simple linear regression or multiple linear regression. That's it. That's the data model. What system theory does is takes it to one level higher called state space data models. State space data models, if you make certain simplification, it drops down to being a regression model. But state space data models are therefore superset, more powerful. It can incorporate the system relationships that I talked about. So then the second half of the book is all about using state space data models for machine learning. And I think it is a very powerful methodology and very accessible. So engineers with an undergraduate degree, when they read this book or look at it from that approach or incorporate state space data models, suddenly they're going to gain a lot, plus understand things in a gut level way. So again, I'm not pitching this, but saying this is what we should do. So as a company, this is really more of a technical advisory. So people who need advisory in digital twins, digital transformation, or machine learning from a systems point of view, I'm there to help them.
Oh, nice. Yeah, well, certainly, as far as the book is concerned, we'll certainly be providing a link to that book in the description below, because I'm sure, like myself, many other engineers watching it would certainly be interested in reading the book. And I'm certainly going to read the book, and probably I'll have to call you back onto the podcast here to discuss more about the book once I've got some deep knowledge behind the contents of the book.
I didn't know, Kudzai, that you're an engineer. If you are, you would love it. It's, we think differently, engineers, and
yeah.
And nobody writes machine learning books from engineers' perspective. Usually written by physicists or mathematics or computer science. They don't learn systems theory the way we do. It's really, and to me, it's the best framework to think about machine learning.
Awesome, that's fascinating. So, Dr. PG, it's been an absolute pleasure having you on the show today. Thank you so much for coming on to share your insights with us.
It's a real pleasure to me to be on. I'm honored that you invited me. I hope your podcast becomes supremely famous and helpful to a lot of people. I really enjoyed it, and thank you very much.
Thank you.